Welcome. This video presents the paper FDS, Frequency-Aware Denoising Score for Text-Guided Latent Diffusion Image Editing, which will appear in CVPR 2025.
Diffusion models are able to generate images by predicting and removing noise from the current image.
Starting from pure noise, repeating this denoising process multiple times gives us a photorealistic image, such as a cat reading a book.
Seeing its generative power, researchers tries to distill a score from diffusion models called Denoising score.
This method, score distillation sampling, originally proposed for 3D object generation, utilizes a diffusion model to provide a gradient direction towards the image distribution and optimize the image. Based on that, delta denoising score is proposed to subtract the gradient of two different prompts, called source and target, enabling image editing. In this example, an image of a cup of coffee is optimized to produce a cup of matcha. However, sometimes their results are not satisfying. For instance, when turning a cup of coffee to matcha, we observe the latte art disappeared.
Similarly, then asking the model to turn a cat to fox, the color of the cat is modified from gray to reddish.
We take a closer look to understand the root cause. Our intuition leads us to examine the frequency domain. To do so, we explore several frequency analysis techniques and ultimately adopt the wavelet transform, which provides multi-resolution analysis in both the spatial and frequency domains. The wavelet transform can be applied iteratively to produce a multi-level decomposition. Initially, an image is decomposed into high-frequency and low-frequency bands, where the high-frequency component emphasizes sharp changes depending on the chosen wavelet filter.
Subsequently, the low-frequency component undergoes additional iterations of this transformation process, repeating multiple times. This results in a multi-resolution decomposition of the original image. This entire process is reversible, allowing for the reconstruction of the original image from its decomposed components. With wavelet transform, we can understand this issue better. For example, starting from an image of a blue butterfly, we would like to turn it into red color.
Here, we visualize the wavelet components from highest to lowest frequency, arranged from top to bottom. Notably, the high-frequency subbands preserve fine details, while the low-frequency component primarily captures coarse color and overall structure. When applying image editing, diffusion models take the input image and use delta score distillation to compute a gradient. This gradient can be further decomposed into different frequency subbands. Interestingly, even though ideally only the low-frequency components require editing, gradients are also observed in the high-frequency components, as visualized in the top right corner. Consequently, the result is a red butterfly, while the intricate structure on the wings are altered. Here is our proposed framework, FDS, Frequency-Aware Denoising Score for Text-Guided Latent Diffusion Image Editing.
Unlike traditional score distillation-based image editing methods that utilize a diffusion model to calculate a gradient for editing the image, we first decompose the original image or its latent representation into frequency subbands using wavelet transform.
Our approach first reconstructs the image using the inverse wavelet transform from the frequency subbands before applying the diffusion process.
The gradient now propagates back to the frequency components. We adopt a gradient truncation operation to prevent updates to the undesired components. With this modification, for example, our method preserves the color and lighting of the stack of stones when transforming it into a Buddha statue, as well as the intricate texture on the butterfly's wings. There are two extreme cases of applying our method that we highlight in our paper. One is color preservation, where we aim to maintain the low-frequency components of the source image. Among all score distillation methods, ours is the only one capable of preserving the object's color, as shown in the highlighted example on the right. Compared to diffusion sampling-based methods, our approach remains competitive. In the second example, where a photo of a man is transformed into a sad man, the baseline methods either alter the color or introduce artifacts. On the other end of the spectrum, we preserve the high-frequency components, which typically correspond to intricate textures, such as the shells of a snail, or detailed structures, like the face and beak of an animal. In these two examples, our method is still the only one that faithfully retains the high-frequency components.
We also take a closer look at how the parameters of wavelet transform affect our results. Specifically, we focus on two aspects: the wavelet level, J, and the filter index, dB. When dB equals 1, this corresponds to the Haar wavelet, which is good at capturing edge transitions. We notice that increasing J leads to a lower resolution in the low-frequency subband.
As the dB index increases, the filters become smoother, which helps reduce mosaic artifacts when the J value is large. Additionally, our method can serve as a complement to other editing techniques that specialize in specific tasks, such as non-rigid editing, pose editing, and mask-guided editing. Beyond 2D, we have explored extending our method to 3D texture editing. Unlike 2D editing, 3D textures exist as fields. To handle this, we use the triplane representation to model the texture field and apply wavelet transformation to the feature planes. Once this is done, we render images from the triplane and perform score distillation sampling.
Our method can preserve the high-frequency texture on a turtle shell when maintaining texture as desired, as well as retain the color of a blanket while adding delicate patterns when needed.
For more details, please visit our website. Thank you for listening.